We're now moving on to look at topics related to assignment 2, in which you are going to perform an analysis of a chosen sport or exercise movement. The topics we're going to cover will certainly build upon the structural information we covered, whereby we looked at the skeleton, the muscular system, and also some of the neurological considerations involved in that also. And we'll introduce a lot of biomechanical principles. So this area of study is what is often called biomechanics. Sport and exercise biomechanics encompasses an area of sports science which is concerned with the analysis of the mechanics of human movement. So it tends to include the description of, analysis of, and assessment of human movement during sport and or exercise related activities. Mechanics really is a branch of physics concerned with describing movement, and in particular how forces create motion or movement. So for us, it's going to be really about how the human body moves in the way that it does, and how the forces that are generated by the muscles and transmitted to the skeleton then create those physical movements. So we're going to be looking at, in terms of that, not just the internal activities of the body, but also the interaction between the human performer and the environment around them. So the transmission of force to outside objects that then creates this sporting action that we see. Two of the key areas we'll look at are going to be areas called kinetics and kinematics, and we'll introduce those over the next few sessions. But it's also important that while introducing these mechanical principles, that we also consider the skeletal, muscular, and neurological factors that we've already looked at to describe the biomechanics of the entire human body. A real fundamental principle of biomechanics is being able to describe and quantify human movements accurately using appropriate terminology. So this relates really directly to learning outcome 4 of this module. And so throughout the coming sessions where we look at aspects of this topic, we really will be emphasizing the key terms that we need to be using. And we'll also be really hammering home the appropriate way of utilizing that anatomical terminology we've already introduced in the module and linking it with mechanical principles, as that will help you achieve way higher on assignment 2. Key pieces of terminology that we should already be aware of by this stage of the semester are listed on the slide here. So first of all, the bones of the human body. Hopefully we should know a wide range of those, such as humerus, radius and ulna within the body. We may also be starting to become more familiar with terms that describe specific aspects of bones. For example, greater trochanter of the femur. If we're not familiar, we will hopefully start to build that across this coming few weeks. On from there, we should be familiar with some of the articulations, by which we mean the joints of the body. We know the classifications of those joints: fibrous, synovial, cartilaginous, and hopefully we know several examples of each. What we will start to need for this coming module is the more specific names. So as opposed to the shoulder joint, if we remember weeks and weeks and weeks ago when there were some presentations prepared by small groups, we started to identify that there are actually sometimes several different joints in what we call, for example, the shoulder. So we have the glenohumeral joints, which is the ball and socket joint we might more commonly known as the shoulder. We also have the acromioclavicular joint. So we need to be familiar with some of those key names. We need to know or we should already know a large range of muscles within the body, and and hopefully quite detailed, and be able to link them to the origins and insertions, which, like I say, should link them to the skeletal system. And we should also be familiar with a good range of movements and the correct terms for those. So we're thinking about things such as flexion, extension, abduction, adduction, circumduction, rotation, and the list goes on and on. These are terms we will have to bring into assignment 2. This is the basis of the human movement, being able to identify these things, and we will start to build upon that to then describe how the interaction of these anatomical terms allows for the creation and transmission of force to the external environment that produces a movement, such as a vertical jump. We're going to start Thursday morning session by looking at this sport and movement. So an athlete sprinting and trying to apply as much of those or as much of the existing knowledge and key terminology to it as possible. So I would like you to try and get a head start at that. So try and put these into groups to look at it. So you should be looking at each limb of the athlete here and trying to describe its position, utilizing the muscles, the bones, the joints and key movements, and trying to link it all together as clearly as possible. So for example, looking at his left leg, we might say that the hinge joint of the ankle is in a plantar flex position caused by a concentric contraction of gastrocnemius inserting upon the calcaneus. Okay, try and do that for each of those joints, and we will, as a group or in a couple of small groups, try and make sure everyone can get a highly accurate description of this movement before we then start to add new subject matter on the day. First part of new information that we're going to add, which add additional methods of describing physical movement, are the planes of movement, also known as the cardinal planes, and the axes of movement. So planes are imaginary positions within which movement occurs, and the axes are straight lines about which objects, body parts, or entire bodies rotate. There are 3 cardinal planes, and each of these is an imaginary flat surface that divides the body into separate sections, and each of which can be used to help us describe movements of the body. So we have the sagittal plane, also known as the longitudinal plane. So this is perpendicular to the ground or vertical, and it divides the body into right and left sides. We can divide it up into the mid-sagittal plane, which would be right through the midline of the body, up through the spine, pretty much. If we took other sagittal planes into other sections of the body, they would be called parasagittal planes. Obviously, they would be parallel to that. The coronal plane is also known as the frontal plane. Again, a vertical plane perpendicular to the ground, and it divides the body into anterior and posterior portions, so front and back. We then have the transverse plane, sometimes also known as the axial plane, which divides the body into superior and inferior portions. So this runs parallel to the ground, almost through the midsection, which separates the top half of the body and the lower half of the body. Movements occur within a plane. So, for example, if this human in the picture was to perform a cartwheel, that is occurring in the coronal or frontal plane. If they were to perform a forward roll, that occurs in the sagittal plane. And if they were to spin on the spot, that is occurring within the transverse plane. An axis is a line about which rotation occurs. So once again, this is an imaginary concept, which can make it somewhat difficult to grasp, but we'll do our best, and we'll talk a lot about it today and again within the in-class session later this week. So we have these three axes that intersect the body. If we're looking at the body as a whole, all three axes will intersect through the center of mass, but we could look at individual limbs, and in those cases we'll treat the axis as going through the center of a joint. So we have the transverse axis or mediolateral axis, which passes through the body from left to right, and the body would spin around that. We have the longitudinal or vertical axis, which passes through the body from top to bottom, so right through the top of the head, down through the center, almost running directly through the spine. And then we have the sagittal or anteroposterior axis, which passes from anterior to posterior, so from front to back. Now, if we use those same examples we had before when discussing the planes, if our individual is doing forward rolls or somersaults, that would be turning around the transverse axis. If we are doing pirouettes or spinning on the spot, we will be rotating around the longitudinal axis. And if we are doing cartwheels, that body will be rotating around the sagittal axis. When we are looking to describe the movement of the human body, movement that occurs in a specific plane will always be around a specific axis. So they're always paired together. So as we see on the screen here, movements in the sagittal plane will take place about the transverse axis. So this is that forward roll. A movement in the coronal or frontal plane will take place about the sagittal axis, cartwheel, for example. And movements in the transverse plane will take place about the longitudinal axis. So this is pirouetting or rotating on the spot. And that's a pretty strict rule. The plane and axis will always be paired. It is unlikely, though, that we will be looking at whole body movements and describing which plane and axis the movement is occurring within and about. It's way more likely that we'll be looking at specific joint movements and piecing together an entire movement through the specific and individual joint actions that occur. But we can quite easily apply the same principle to those. So the diagram we see on screen here is a barbell bicep curl. In this action, we have flexion of the forearm at the hinge joint of the elbow, and in this situation, movement occurs around the transverse axis, so that in this situation, rather than going through the center of the body, the axis, that imaginary line, is going from left to right, right through the center of the elbow, and movement is occurring in the sagittal plane, that plane which divides the body into left and right sections. In fact, anytime we see flexion or extension, because they're always forwards and backwards movements, they will always be within the sagittal plane and about the transverse axis. In this example, we see a dumbbell lateral raise being performed. So this involves abduction of the arm occurring at the glenohumeral joint within the shoulder due to an isotonic concentric contraction of the deltoids. Now, this movement is occurring about the sagittal axis and within the frontal plane. It would be followed by adduction as the arms return back to the sides of the body about the same axis and within the same plane. So adduction, abduction will always occur within this plane and about that same axis. So sideways actions will be always within this situation. So always sagittal axis, frontal plane. So adduction, abduction, lateral flexion, inversion, eversion. If we think about this in a more full body movement situation, taking side steps, imagine a tennis player shuffling left and right across the baseline, awaiting a return. And for a third and final example, we can see here an individual performing Bantes, in which we are externally rotating the humerus at the glenohumeral joint of the shoulder. Here, this sort of rotational movement is occurring about the longitudinal axis and within the transverse plane. So this is key. Any rotation at all will always occur within the longitudinal axis and within the transverse plane. Whether this is rotation of an individual body part, we could also add in this because it's also rotational movement, supination and pronation of the forearm, or whether it's rotation of the entire body by spinning on the spot. It is always these two paired axis and plane. Our knowledge of movement at human joints can be further developed by understanding lever systems. Within the human body, our bones act as levers. Joints function as the fulcrums or the pivot points of these levers. So a lever can be defined as a rigid body that moves around some fixed point, that being the fulcrum. And any individual lever will be acted upon by two distinct forces: the effort, which causes movement, and the resistance or load, which opposes the movement. So within the human, the load or resistance will be represented by the specific body segment plus any extra weight or equipment being lifted. So for example, within a bicep curl, the load will be the weight of the forearm and hand plus any additional weight held in the hand, such as a dumbbell. The fulcrum will be the joint around which the movement occurs. So again, in that bicep curl example, the fulcrum is going to be the elbow, and the effort is the force or the internal force created by the working muscle or muscles to create the action at that joint. And again, in the bicep curl, that will be biceps brachii. Levers can be categorized into three types, and this depends upon the position of the fulcrum, the effort, and the load in relation to each other. When the fulcrum is between the effort and the load, we have a first-class lever system. So it's your classic seesaw arrangement. First-class system can produce what's called either a mechanical advantage or disadvantage, depending on whether the effort or resistance is closer to the fulcrum. So if the load is closer to the fulcrum than the effort is, we are going to require less effort to move the load. So for example, if the load is 10 kilograms and that is closer to the fulcrum, we will have to apply a effort of less than that 10 kilograms to shift the seesaw in our favour. There aren't many first-class lever systems in the human body. One example is the lever formed by the head resting on top of the vertebral column, as we can see in the diagram. The resistance is provided by the weight of the skull. The fulcrum is the joint between the atlas and the occipital bone. So this is called the atlanto-occipital joint. And the effort comes from the posterior neck muscles. And the action of lifting the chin up, nodding the head down, would be the seesaw action of the first-class lever system. In a class 2 lever, the resistance is always between the fulcrum and the effort, or the load is always between the fulcrum and the effort. This sort of lever system is similar to what we see in a wheelbarrow. So the fulcrum will be the wheel, The load is whatever we put in the barrow itself, and the effort would be the human lifting the handles at the end. So this sort of lever system always gives us what we call a mechanical advantage, because the resistance is always closer to the fulcrum to the effort. So we have to put relatively less effort in to lift a given load. So ideally, this would be the perfect sort of lever system that we'd want in the body, because we have to put a relatively small amount of muscular effort in to lift a given weight. As with the Class 1 lever system, there are very few Class 2 levers within the body. One key example shown here would be performing the calf raise exercise. The fulcrum for such a movement would be the ball of the foot. The load, or the weight of the body, plus perhaps a barbell placed across the shoulders, acts down straight through the center of the body, almost through the tibia towards the floor, and the effort is applied by gastrocnemius and soleus, or the calf muscles, performing upwards. When we rise up onto the toes, we're rotating around the ball of the foot, and that effort goes up through the calf. And because, as I said before, this puts us at a mechanical advantage, we can lift a relatively large amount of weight in a calf raise compared to our body weight. Class 3 lever systems are the most common levers in the human body. Third class levers always produce a mechanical disadvantage because the effort is closer to the fulcrum than the resistance. In the body, this sort of arrangement favours speed and range of motion over force production. So in order to overcome the given load, we will have to produce a disproportionately large amount of effort. But as a result, we'll be able to move through a much bigger range. Performing a bicep curl is a great example of a third class lever system within the body. The load to be overcome is the forearm, hand, and weight of the dumbbell or barbell which is being held combined. The effort is being applied by the biceps brachii muscle via its insertion point on the radius, and the fulcrum is the elbow joint. Lots and lots of other examples in the body. So, for example, hip flexion, where we are lifting the lower or the leg up in front of the body. In this situation, the load is the entire weight of the leg. The effort is being applied by the hip flexors inserted on the femur, and the fulcrum would be the ball and socket joint at the hip. Within the previous slides, I mentioned this idea of mechanical advantage a few times. Mechanical advantage refers to the general effectiveness of a lever system in moving a given resistance. It refers really to this concept of leverage. And so what lever systems have is a trade-off sometimes between effort and speed and range of movement. In one situation, the lever operates at a mechanical advantage, so it has leverage. So a less forceful effort can move a more forceful resistance. The trade-off is that the effort has to move further. So there must be a bigger range of motion in order to move the resistance a smaller amount. In the opposite situation, the lever operates at a mechanical disadvantage, so we have to produce a much more forceful effort to move a smaller level of resistance. So the trade-off there is that the effort moves over a shorter distance and less quickly, but the resistance will move further. More simply put, really, the longer the lever arm is, the less force is required to overcome the resistance. And there's a few real life scenarios that illustrate this one quite nicely. So the two pictures represent real life scenarios in which we utilize this mechanical knowledge of lever systems to our advantage. Um, so in a wheelbarrow, we have the fulcrum being the wheel, the load sits within the barrow, and the effort is applied at the far end via the handles. Um, this means because the lever length for where we apply effort is as far from the fulcrum as possible, it requires a relatively small amount of force produced by the human to lift and then move the load which is carried within the barrow. We then have a tire iron used for anyone's not familiar, for loosening the nuts on a tire if you're going to change the wheel. The fulcrum would be where the bolt is on the wheel. The load is pretty much maintained within that point because the effort required to turn that nut, and the actual effort is applied on the very far end of that tire iron. So we can, and the longer that tire iron is, the easier it would actually be to turn the bolt. So we use this in various situations in general life. The further away from the fulcrum we can apply the effort level, the easier it should be. A nice example of something I'd like to use would be opening the door. So on a door, the fulcrum would be where the hinge, the load is the weight of the door, and the effort is whichever point you pull that door. So what you find is the handle is placed on the far end of the door, as far away from the hinge as possible, which makes it very, very easy to open a door. If the handle is placed at the other side of the door, right by the hinge, you would have to apply a much greater amount of force to open that door. So by placing it at the far end of the door, we create leverage and a mechanical advantage to do so. In sport, really skilled athletes will maximize lever length in order to maximize the amount of torque produced, torque being rotational force. We'll come back to that in a week or so. So, for example, the two pictures on screen show situations in which we're striking the ball. The ball being the resistance that is to be moved. So we create as long a lever as possible by, for example, in a tennis serve, striking the ball at the highest possible point. So we've got this huge lever length going from the shoulder to the very end of the racket. And again, in the baseball, extending the arm, striking the ball towards the end of the bat. By doing so, we are able to generate massive amounts of force upon the projectile. Now, unfortunately, as was mentioned a little bit earlier, the vast majority of lever systems in the body are class 3. This therefore means we are almost always at a mechanical disadvantage. The picture shows a lateral raise. In this situation, the fulcrum will be the ball and socket joint at the shoulder. The effort is being applied via the deltoid, which inserts at the proximal end of the humerus, so very, very close to the shoulder joint. So we don't have a very big lever length there. And the load is provided by the weight of the arm plus the dumbbell is being held in the hand. As a result, for anyone of you who has performed a lateral raise, you probably aren't able to shift a huge amount of weight. Now, we can manipulate lever length in this situation, or for want of a better word, cheat the lift. If you bend the elbows, the weight is brought closer to the shoulder and you're probably able to lateral raise a bigger load. In reality, you're probably not changing much of the force that has to be produced. If you put the arm straight, you'll be lifting a lower load, but probably generating the same degree of force to lift it. Earlier on, I showed this image and asked that you start to begin to think about the anatomical factors related to it. What we will then do, having established that hopefully highly accurately, is start to think about the lever systems that are in play. So feel free to start thinking about that, and we will discuss in a much more detailed fashion on Thursday in class.